The paper I want to share is BioMD, all-atom generative model for biomolecular dynamic simulation. Okay, the molecular dynamics is essential for computational chemistry and drug discovery, but it faces critical bottlenecks. The first one is quadratic scaling. Non-bounded forces like Coulomb forces or van der Waals forces scale quadratically with atom number. The second is femtosecond time step. High-frequency vibrations can limit accessible timescales. And the computational cost of microsecond to millisecond processes require intensive resources. But this timescale is typically the timescale of some real-world biochemistry processes. But there are also some challenges in the ML-based molecular dynamics. The first category of ML-MD is to generate the conformation ensemble directly. It is static, so it is time agnostic. We cannot get kinetic pathways from the conformation ensemble. The examples of this category contains AlphaFlow and BioEmu. The second category is trajectory modeling. For example, the NeuroMD, which treats the protein as a static thing but simulates only the dynamics of ligand. And the MD-Gen is designed only for peptides and proteins, but it cannot handle small molecules. So these things cannot generally handle protein-ligand interactions. So currently, no method generates a full atom trajectories for protein-ligand systems with temporal evolution. In this work, the authors propose key observations that conformational changes are subtle over short timescales, but it involves significant global movement over long timescales. So BioMD provides a hierarchical decomposition into two stages. The first is coarse-grained forecasting. It generates large step conformations, for example, every 10 steps. And then it is the fine-grained interpolation. It fills the intermediate frames between different anchor points. We can see this figure. So left part, subfigure A, is a hierarchical framework showing the two-stage processes. The blue part is a coarse-grained forecasting process, which generates the anchor frames xk, x2k, and so on. And the yellow part is fine-grained interpolation, which can generate the intermediate frames between two anchors. So this kind of decomposition reduces the sequence length and manages error accumulation. Also, this framework uses flow matching-based models to generate the geometries. So in the right part, the figure B is the time scheduling for forecasting and interpolation tasks. So in this figure, we can see there are two time axes. The first time is t, which is physical time of simulation. The second so-called time is the tau, which is corresponding to the flow matching methods. Or it can be called as the noise intensity, where the tau equals to 1 is the clear geometry and tau equals to 0 is the pure noise. So we formulate the non-frames as noise-free frames, which assign them to tau equals to 1 or unmasked things. Then we generated frames from noise, or tau belongs to 0 and 1, which is masked. The independent noise is applied to each frame following the diffusion forcing framework. So in this work, for the two stages, they use a unified framework which contains the same model but trained under different masking schedules. Here I will give some notation. The first is X, which is a trajectory sequence containing L frames of atomic coordinates. The lower script is a physical time t. Also, the upper t, which is a set of tau, is a time step vector, where each tau of the t is sampled from the uniform distribution between 0 and 1, which controls the noise level for frame I. Also, we have U, which is the ground truth velocity field for the sequence. Here, the velocity field, we can see it is superscript with tau. So this is the flow matching velocity rather than the physical velocity of the system evolution. Also, we have C, which is the static conditioning information, like initial coordinates, amino acid sequences, or atom types. The noise masking method is for each frame, we independently perturb them by the noise level. Tau belongs to 0 and 1. This is exactly the noise injecting schema in the flow matching method. So given these definitions, the training objective is the mean squared loss between the predicted and the ground truth velocities. Here, U theta is a flow matching model which predicts the denoising velocities. Yeah. And it generates the velocities for all frames simultaneously. For stage 1, we have coarse grain forecasting. The sequence to predict is the sequence x0, k2k, and so on with k equals to 10. And the initial frame is fixed, which is x tau 0 equals to 1. And for the other frames, we sample the noise intensity in the uniform distribution and try to denoise it. For the inference time, we sample the tau equals to 1, which is fully noised and denoised to the generated geometry. We can have all at once or autoregressive inference strategies. By all at once, it means we generate xk, x2k, x3k at the same time. But for autoregressive, we generated xk dependent on x0 and x2k dependent on xk and so on. The stage 2 is the fine-grained interpolation. Here, the input segment is xi, which contains the 10 frames between xik and xi plus 1 times k. Here, the yik is the block of intermediate frames to be generated between the two anchors. Here, by blocks, it means we have multiple lower scripts which corresponding to the physical time. And for anchor frames, the denoising time is fixed to be 1, and for intermediates, the noise is sampled from 0 and 1. So for the interpolation, we have x tau, y tau, which is the predicted intermediate frames as the noise level tau for the block, and xt is the full noise segment. Here, the t is a set of noise labels, noise intensities, or flow matching time. This includes the fixed anchors and noise intermediates, and this sec is the sequence conditioning information. For flow matching part, it uses Euler method, ODE integration, which directly added the delta tau times the u theta to the y tau to get y tau plus delta tau. The model simultaneously generates all k-1 intermediate frames by integrating from tau equals to 0 to tau equals to 1, which is the cleaned coordinates, conditioned on the fixed angle point. So the velocity model uses all atom Cartesian coordinates and has these three components. The SE3 graph transformer is used to encode the initial conformation. It can produce single representation and pair representation. Then the full trajectory transformer is the core generative module. It adapts the attention pair bias and temporal attention for combined spatial temporal modeling. This architecture is tailored for generating trajectories from a single initial structure. Here is the experimental part. This is tested on two datasets. The first is Misato, which contains 20,000 protein ligand trajectories and 100 frames each per 8 nanosecond MD, which simulates the ligand dynamics within the pocket. And the second is DD13M. It contains 26,000 dissociation trajectories and around 480 frames each, which simulates the ligand binding. The baselines are chosen to be denoising LD, GNN-MD, Verlet MD, NeurMD, and static methods. It evaluates using these metrics. The first is physical stability, for example, whether it can model the correct bond length, the angle measured by MAE, or whether it will recover the steric clash or not. The second is the flexibility, whether it can recover the RMSF, which is the root mean square fluctuation, and the Pearson correlation. The third is whether it can predict the unbinding. We can measure the success rate and the path RMSD. Here is the ligand RMSF on Misato datasets. The blue line is the ground truth, and the green and red curve are two different settings of BioMD. We can see that for most of the cases, the BioMD is the most similar to the ground truth curve. It achieves the highest correlation with the reference trajectories. So this shows it can accurately capture the dynamics behavior and conformation flexibility. Here is a detailed result. We can see in most of the cases, the BioMD show better results to the baseline methods. And we can also see that for the geometry recovery, the BioMD real by using relative coordinates often perform better. But for RMSF recovery, the BioMD ABS or use the absolute coordinates often perform better. Here is the case study of a special case. We can see that the BioMD can in general recover most of the distribution of the ground truth MD. And the DD13M is for ligand unbinding. In this case, it finds that autoregressive strategy is critical. For non-autoregressive, we can observe minimal ligand movements when average overpass, but for autoregressive 5, which uses 5 previous frames, we can see significant improvement in path accuracy. So when measuring binding success rates, we can see it almost can predict all of the correct unbinding processes within 10 attempts. Also, it achieves significant computational efficiency. For example, for metadynamics, it may need 1 hour to find the first pass, but for BioMD, it takes only 10 seconds and 50 coarse grain steps per pass. For example, the subfigure A is the input information, which is a bound state, and the B are two different BioMD generated pathways. It can either reproduce non-pathways, but it can also predict novel pathways, which is circled in green circle. And the subfigure C is a reference metadynamics pathways, which is simulated within 1 hour. So, dependent on this experiment, the author analyzed the trade-off and error accumulation in different scenarios. First of all, autoregressive or not. Autoregressive enables long-range dynamics, but it introduces the error accumulation. But geometry errors remain manageable. For example, under 0.1 angstrom for bound and 0.1 radius for angle. And this error can also corrected by local refinements, which is the alpha-fold cell relaxation. Also, we can use relative or absolute coordinates, dependent on the experiment results. We can see the absolute coordinates show superior global conformational landscape, but have higher protein RMSF correlation, and can predict accurate centroid pulse RMSD. So this is best for reproducing non-dynamics. But when using relative coordinates, this encourages exploratory behavior, and it produces this higher unbinding success rates. Also, it can preserve local chemical fidelity. So this is best for sampling large-scale changes and discovering novel events. So this BioMD is the first atom generative model for long timescale protein ligand dynamics. It proposes a hierarchical forecasting plus interpolation framework, and it uses the unified conditional flow matching with the noise as masking. For both stages, it uses dual attention architecture for spatial temporal modeling, and it can suitable for flexible generation modes, for example, for exploration or for better accuracy. And in result, it shows some plausible results. For example, it gets high unbinding success rate on DD13M. It shows orders of magnitude faster than metadynamics. And it is physically plausible conformations with high flexibility correlation. But so now I think in the predicting framework, we didn't consider the potential energy and the classical velocity or forces at all. So we just predict everything trained based on data sets. So I think maybe, for example, we can introduce, for example, sorry, for example, the force alignments or the between different timescales or velocity, momentum between different time scale, between different time step and interpolation. This may achieve higher data efficiency to cooperate physical things. Also, this can also be reflected by the results in the in here. When it incorporates the 5 frame to do autoregressive generation, it introduces significant improvement. I think this might show that for the 5 previous frames we can infer the velocity information. So this may help to predict more accurately. So maybe directly introduce velocity and force information can also be helpful. Thank you. Thank you for listening, and please comment if you have anything to discuss or any suggestion. Thank you.